This is the video lesson for concept 35, interior and exterior angles of polygons. Don't forget to write your name. Next thing you're going to do is write concept 35, so it's easy for us to track. And then here's the first main idea: the sum of interior angles of polygons. The sum of the degrees of any polygon can be determined by the number of triangles that can be drawn within the polygon. Complete the table below and look for a pattern to find the sum of the degrees in any polygon. So let's start with our first one here. Okay, we have a triangle. This one we're familiar with from our previous concept. We have three sides, of course, and it is a triangle, so it's only one triangle. And then the sum of the interior angles is 180 degrees. Our next shape is a quadrilateral. Okay, quadrilateral, this should be semi-familiar from previous discussions we've had. It's just a polygon with four sides: square, rectangle, and so on. Okay, the number of triangles that can be drawn within a quadrilateral without any overlapping dashed lines. Okay, because if I draw another diagonal this way, okay, I will overlap this first dashed line I have here. So when we say the number of triangles within a polygon, it's only those without any overlaps. So here I can only draw two triangles. Okay, that's where this 2 comes. The sum of the interior angles for a quadrilateral is 360 degrees. Next one, it's a pentagon. A pentagon is a polygon of 5 sides. The number of triangles I can draw within a pentagon without any overlaps is 3, and the sum of the interior angles here is 540 degrees. Next I have the hexagon. This is a polygon of 6 sides. I can draw 4 triangles, okay, within a hexagon, and the sum of the interior angles here is 720 degrees. The next one is a heptagon. Okay, this is a polygon of 7 sides, and the number of triangles that I can draw within a heptagon is 5, and the sum of the interior angles there is 900 degrees. Next one, for my UFC fans, is the octagon. Okay, this is a polygon of 8 sides. The number of triangles I can draw within it is 6, and the sum of the interior angles of an octagon is 1080 degrees. So let's pause for a bit and let's look at our table so far. The number of sides for each polygon has of course increased by 1, 3, 4, 5, 6, 7, 8. The number of triangles within each polygon has also increased by 1, 2, 3, 4, 5, 6. And you would have noticed that the number of sides to the number of triangles within each polygon has remained constant too. Each polygon has the number of sides has always been greater than the number of triangles by 2 for each quadrilateral. So sorry, for each polygon. Okay. Also, the sum of the interior angles for each polygon as we've gone, increasing the number of sides, has increased by 180 degrees. 360 is double 180. 360 plus 180 is 540. 720 plus 180. 540 plus 180 is 720. 720 plus 180 is 900, and then 900 plus 180 is 1080. Okay, this pattern here is gonna hold for our last 2 shapes here. Okay, the nonagon, which is a polygon of 9 sides, and the decagon, which is a polygon of 10 sides. The number of triangles in a nonagon is 7. 9 minus 7 is 2, right? So it still holds. And then the number of triangles inside a decagon is 8. How would you figure out these two? Well, 1080 plus 180, because each one has been increasing by that much, is 1260, and then 1260 plus 180 is 1440. So we found these features now of the first 10 polygons, referring to the number of sides here. Okay, so the sum of interior angles formula. Okay, if n represents the number of sides of a polygon, then the sum of the interior angles s, we call that s, can be found using the formula s is equal to n minus 2 times 180. N minus 2 because the difference again from the number of sides to the number of triangles drawn within the polygon is 2. Okay, n being the number of sides, and then 180 degrees because each as we increase the number of sides in each polygon, we also add 180 degrees between each one. Okay, so that's where the formula is derived from. So this last part here, the interior angle of a regular polygon. Okay, a regular polygon is one in which all sides are congruent and all angles are congruent. To find the measure of an interior angle in a regular polygon, okay, we use this following formula: s divided by 2. Okay, this is the measure. Maybe I should have started like this. This is the measure of an interior angle. S is the sum of the interior angles. Okay, that comes from here. It's this formula. That's what S is. Okay, and then you divide by 2. Divide by, or in this case, number of sides if we generalize. Okay, so that's what this formula here is. So please note the difference. If the question is saying what are the sum of the interior angles of the following polygon, you're using this formula here. If the question says find the measure of the interior angle of a regular polygon, you're using this formula here. This is not 2, I apologize, this is S over N, okay, the number of sides. Next page. We have our practice problems. So number 1 says find the sum of the interior angles of a 15gon. Okay, so this is how they use the notations after decagon to refer to what type of polygon or the number of sides of the polygon we're talking about. So this is just that first formula we're using, and then maybe it's useful, okay, if I write this formula here up on top so that's easy to refer. So S is equal to N minus 2 times 180 degrees. So right here I have S is equal to, I have a 15-sided polygon, so 15 minus 2, okay, from my formula, times 180 degrees. Use PEMDAS, parentheses first, 15 minus 2, I get 13 times 180. Put this in your calculator and you're going to get 2,340 degrees. So then the sum of a 15gon, the sum of the interior angles of a 15gon is 2,340. Number 2, find the sum of the interior angles of a 21gon. Same idea, plug into your formula. I have 21 minus 2 times 180. I get 19 times 180, and that's equal to 3,420 degrees. Number 3 says, what is the measure of each interior angle of a regular pentagon? So this is the second formula. So this is measure of interior angle. S over, and I keep writing 2, what I keep writing 2 is S over N. Number 3, so regular pentagon, you can refer back to your table here. It's a polygon of 5 sides. Okay, and then the sum, we need S. The sum, we don't need to find it, we can, but it's already given to us here in our table. The sum of the interior angles is 540 degrees. So I'm going to do 540 divided by 5. So S over N is equal to 540 divided by the number of sides, 5. Okay, and that's going to give me 108 degrees. Similarly, what is the measure of each interior angle of a regular 18 gun? We don't have this one in our table, so we do need to figure out what would be the sum of the interior angles. So S is equal to 18 minus 2. I'm using the first formula here to find that measure of the interior angles. This is 16 times 180, and this gives me 2,880 degrees. We know how much sides we're working with here. It's 18. So the the measure of one interior angle therefore is S divided by N. Sum is 2,880 divided by 18, the number of sides, and then this is going to give you 160 degrees. Next idea, I have the exterior angle sum. Exterior angles are always supplementary to their adjacent interior angle. On the polygons below, find the measure of each exterior angle along with the sum of all exterior angles. So what this first sentence means, okay, is the same idea we've been working with when dealing with angles, lines, and exterior angles. Okay, I'm going to use blue here. Okay, exterior angles are always supplementary to their adjacent interior angle. This here is a straight line, therefore this red angle and 79, okay, they will add up to 180 degrees. Similarly, that's another straight line there. Okay, so this outer angle with this 40-degree angle there, okay, are going to add up to 180 degrees. And then this one here, 61 degrees, with this outer angle there, are going to add up to 180 degrees. Okay, this is a theorem. Okay, so if they add up to 180 degrees, I can find each exterior angle. Okay, you can put these in your calculator. Okay, you'll have 180 minus 79. Okay, this is going to give you 101. So this angle here is 101 degrees. For this one, okay, I have 180 minus 40. Okay, and I'm going to get 140 degrees. And the way you verify is add them up. 140 plus 40, that's 180. 79 plus 101, that's 180. And then finally this one, 180 minus 61. Okay, that's going to give me 119 degrees. Okay, so 119 plus 101 plus 140, these add up to 360 degrees. Next one, same idea. Okay, we had a triangle in this first case, now we have a quadrilateral. Okay, and it's still, whoops, I drew that one in red, I meant to draw it in blue, apologize for that. So that's a straight line there. Here's another straight line, another one, and these are all supplementary. Okay, and remember, supplementary, let's go ahead and annotate, even though we already did that first example. They add up to 180 degrees. So same idea, do 180 minus that given angle there, and that gives you the value of that exterior angle, so I have 104 degrees there. I have 180 minus 89. This gives me, this angle here is 91 degrees. This angle here, you got 180 minus 71, and I get 109 degrees. And then that last angle there, I have 180 minus 124, and I get 56 degrees. Okay, so I know it looks a little messy here. Let me just put a box over all the angles I found here, and then the final answer is adding all these up. So 109 plus 56 plus 104 plus 91, and this, when you put that in your calculator, you get 360 degrees. Next one, I have a pentagon, so I'm going up in the number of sides here for each polygon. I had a triangle, 3 sides, quadrilateral, 4 sides, pentagon, 5 sides. Okay, so I'm going to do the same thing. Okay, I'm doing the same thing. I'm finding the measure of each exterior angle. You're going to take each one and subtract from 180 degrees, just like you did in these previous two. So 180 minus 87, 180 minus 121, 180 minus 98, 180 minus 104, 180 minus 130. When you do those, you're going to get 93 degrees, 59 degrees, 82 degrees, 76 degrees, and 50 degrees. When you add all these angles up, you're going to get 360 degrees. Next one, hexagon, is a 6-sided polygon. Okay, same idea. Subtract each of these given interior angles from 180 degrees. That's gonna give you the measure of the exterior angle. When you do that, you get a 68 degrees there, 56 degrees there, 51 degrees there, 65 degrees there, 63 degrees there, and 57 degrees there. When you add up the red angles, the exterior angles, okay, you're gonna find that it's 360 degrees. Okay, so going back to this first main idea here, and what we just shown here is that regardless of the polygon you're working with, okay, the number of sides does not matter. Okay, the interior angles do give me a particular sum, as we shown in our table from this first part, right? The interior angles are different depending on the polygon you're working with, but for the exterior angles, they're always going to add up to 360 degrees. So we can write that in for our conclusion here. The sum of the exterior angles of any polygon, regardless of sides, is 360 degrees. Okay, this final set here is practice on that idea we just talked about. What is the measure of each exterior angle of a regular hexagon? So hexagon, so there's a key word here. Okay, what is the measure of each? Okay, so don't make that mistake. Let's underline it. Okay, each exterior angle of a regular hexagon. That does differentiate from the conclusion of the sum of all exterior angles. The sum of all exterior angles is always going to be 360. So we need to find each exterior angle. Okay, so it's a regular hexagon. We already defined what regular meant. Regular meant that all sides and angles would be the same. Okay, so we know that the measure of the exterior angles will be 360 degrees. Okay, and because it is regular, that means that all the angles would be equal. So you can divide the sum of the exterior angles by the number of sides, okay, because a hexagon is a 6-sided polygon, and then that gives you 60 degrees, the measure of each exterior angle. Number 6, what is the measure of each exterior angle of a regular 24gon? So it's the same idea, just the number of sides of this polygon has increased. Okay, so 360 divided by 24, and again 360 because that's the sum of all exterior angles for any polygon. That's the number of sides of this polygon, and that will be equal to 15 degrees. Number 7, if the measure of a regular polygon measures 12 degrees, okay, so they give us the measure of the exterior angle. Okay, this one's a little different. How many sides does the polygon have? We can actually find how many sides a polygon has given the measure of the exterior angle and knowing that it is regular. Okay, and the way you do this is it's the same formula, except we now just have a variable. We know all sides, all exterior angles, sorry, add up to 360. We don't know how many sides it has, so we call that x. But we do know that the measure of each one is 12. Okay, now I solve for x, and how do I do that? I multiply both sides by x. Okay, because I'm solving for x. They cancel out on that side. Whoops, I meant to draw that through there. Okay, and I get 12x is equal to 360. Then I divide by 12, and then you'll find that x is equal to 30. So this is a 30gon. Okay, when the measure of each exterior angle is 12. So you can write here, this is a 30gon. Last one. If the exterior angle of a regular polygon measures 40 degrees, how many sides does the polygon have? Okay, same idea, 360 degrees divided by the number of sides, that's what we're looking for, and we know they add up the exterior angles. Each exterior angle is 40 degrees. Solve for x, multiply both sides by x. I get 40x is equal to 360. Divide both sides by 40, and I get that x is equal to 9. So this is a nonagon. Okay, and this wraps up concept 35.